All right, first off, a couple of actually one reminder. Today's the deadline for regrading requests for the free response part of test number 2. So far, I just received one request, and I have already replied to that request. So, if you have submitted a request, or if you have forwarded an email to me or a chat that haven't replied to, kindly let me know. Maybe it went to the spam folder, but only one person asked me to take a look at his or her free response part, and I already replied to them. So if you still have some questions, I think you still have until midnight tonight to send me your regrading requests. Otherwise, we will not accommodate any more regrading requests. All right. And then for today, we'll finish worksheet 11. Remember, what we are doing here is that we started off this week by looking for the intervals of increase or decrease for a certain function. And we said that is just finding the sign of the first derivative over the subintervals, which are defined by the critical numbers, meaning those that will make f prime equal to 0 or undefined. Okay. And then we also look at last Wednesday on finding the local extreme values of your function. And this would be basically looking at the critical numbers and either applying the first or the second derivative test to them to find the maximum and the minimum value. But I guess we stopped at example. I don't remember exactly where we stopped, but in the annotated version of the notes that I have already uploaded in my website, I already included problems solution until problem number 6. But I know I skipped some of these last time. So I hope you tried answering them and compared your solution with mine. Also double check my arithmetic there. Let me know if there are some mistakes in there, so that I can correct the notes. All right. Okay, and now let's work with problem 7. Let me just review the instruction here. We need to find the critical numbers, the extreme values, by applying the first derivative test. Hold on, Daniel has a question. Which problem is this, Daniel? From worksheet 11, the answer was x equals 5. Let me see. Is it finding the local max and the local min? Oh, here we go. I think it's example 2. All right. So in example 2, yeah, what the actual solution then, and how you would know to use both. Okay, in this particular problem, you are not told which test to use, because I think it's straightforward how to find f prime, to find the critical numbers. But to classify the point or the critical point, you need to use either the first or the second derivative test. If the problem didn't tell you exactly what test to apply, then you are free to use which one is more convenient to you. So I guess here, which one is easier? I guess it's easier to use the second derivative test. So if I will personally be answering problem 2, I'll go with the second derivative test. But since the problem is silent as to which test to apply, you could have also used the first derivative test. So it's up to you which one to use. Eventually, they will give you the same answers. Oh, by the way, oh yeah, I remember this one now. Actually, the second derivative test will be inconclusive. So that means if you started, yeah, they will give the same answers, but in this example, the second derivative test is inconclusive. So you will have no choice but to use the first derivative test. But if the second derivative test happens to be conclusive, or it gave us a conclusion, then it will have the same answer as the first derivative test, right? I guess somebody wrote in the chat last time, the first derivative test will require you a little bit more work in general, because you have to plug in test numbers, because you need to look at the sign of the derivative from the left and from the right. So it will require you a little more work, but it is guaranteed to always give you an answer. But the second derivative test will fail if the second derivative happens to be 0. Look at solution 2. If you plug in x equals 5, you get 0 or undefined. And so the second derivative test would be inconclusive. Right. Yeah. Well, we say second derivative test is inconclusive. It doesn't mean anything. It's just that the second derivative test fails to give us the answer. So it still can be a local max. It still can be a local minimum. It can be neither. But the point is the second derivative test cannot tell us which one. So you need to resort to other tests, such as the first derivative test. But the good thing about the first derivative test, even though it entails a lot more work generally than the second derivative test, it will always give you one of three conclusions. Either you have a local maximum, you have a local minimum, or you have neither a local max nor a local minimum, right? It will never result into an inconclusive test. So yeah, there's no hard and fast rule to determine which one would be easier. Sometimes it's just how the function looks like. So I cannot give you a checklist which one to choose, but from experience, I think you will know which one would be better to use. Okay. All right, but if you go to problems 4 to 6, it requires specifically the use of the first derivative test, so we don't have any choice. Otherwise, you might not get credit if this was a homework or a exam problem if you use the second derivative test. So make sure to read the instructions carefully. So I guess last time we saw that much of the solution are algebraic manipulations, plugging in, simplification. So I guess I skipped some of them, but hopefully you take some time to try to answer them on your own and then compare your answers with mine. I'll go with a more interesting problem, which is problem 7, which upon seeing the function, you will already know that this will require more work because I guess by now we are used to expecting a lot of work to be done whenever we are working with piecewise or conditional functions, right? So here, let's find the critical numbers and then classify them for f. Right? Well, still the first step is to find f prime. But here, f is actually a conditional function. So here, f prime would be another conditional function, okay, defined on each of the intervals given, but on the boundaries, we need to be a little bit careful. So what do I mean? So if we'll take the first function, the first function or the first piece of the conditional function is x plus 9. The derivative of x plus 9 is 1. So the derivative would be 1 whenever x is between x and -3. Okay, so take note that here I removed the equal sign for the left endpoint, because remember, for the derivative to exist, you should be able to get the left hand and the right hand derivative, right? The derivative coming from the left and the derivative coming from the right. But the problem here is we don't know how the function looks like to the left of 8, right? So we cannot solve for the derivative coming from the left of 8. So that means we are not sure whether or we are not sure what is really the derivative at x equals -8. Okay, so that's why here in my f prime, I don't have a value for f prime of -8, but I know what would be the derivative to the numbers very, very close to the right of -8. Right? And I guess you will see the pattern that I am always removing the equal sign. Right? So okay. Next, if you look at the second component function here, or the second piece, we have x squared plus x. The derivative is 2x plus 1. But this will only apply for x's strictly between -3 and 2. Right? Note here, the second condition applies to x's between -3 and 2, with -3 and 2 included. But the derivative will only be true for x's strictly between -3 and 2. Because remember, at x equals 3, we need to take a look at the derivative from the left and the derivative from the right. If those two derivatives are equal, then that's the value of the derivative. If they do not agree with each other, then the derivative is undefined, right? So that means in order to find the derivative at x equals -3, we need to take a look at the derivative coming from the left and derivative coming from the right. But recall how to compute the derivative coming from the left. This is the limit of f of x minus f of x plus h, sorry, minus f of x all over h as h approaches 0 coming from the left. And if you're looking for the derivative coming from the right, you just change the minus sign there and you take the derivative the limit as h approaches 0 coming from the right. Okay? But so that's by definition the one-sided derivatives. But of course, we want to avoid using this limit definition. There might be a shortcut. And remember a shortcut we used for finding the derivative of piecewise functions at specific numbers on the boundary? There's a shortcut, but the shortcut requires the function to be continuous, right? So let's see if this is continuous at x equals 3. So this function, let's see. So what's the limit of f of x as x approaches -3 from the left? So if we're looking for the limit of f as x approaches -3 coming from the left, we look at the function that will apply to x is very, very close to the left of -3. And that would be x plus 9, right? So this would be the limit of x plus 9 as x approaches -3. So this will be equal to 6, right? Then let's see what's the limit of f of x as x approaches -3 coming from the right. So coming from the right of -3, we'll go to the second condition. And the limit of x squared plus x as x approaches -3 would be 9 minus 3. Oh, there we go. That's also equal to 6. So here, by this quick check, we see that f is continuous at negative. So when your function is continuous at a specific number, it follows that the derivative coming from the left of -3 will just be the derivative of the left function evaluated at -3. But obviously, the left function has derivative 1 if you plug in -3, but there's no x to plug in there. So the answer here is 1, right? Then if we take the derivative coming from the right of -3, we'll use the function to the right, or the derivative of the function to the right. If we plug in -3 here, what do we get? We get -6 plus 1, so this is -5. And look at this. The two one-sided derivatives are not equal to each other. So therefore, we say that the derivative is undefined, or it doesn't exist at x equals -3, precisely because the left-hand derivative is not equal to the right-hand derivative. Okay? Does that make sense? That might be a lot to take in, but yeah, before I proceed, any question? And now I think you are now expecting a very long solution whenever working with conditional functions. And you see the intricacies, the technical details that I have to go through before, say, before finding the derivative at the boundary point. The crucial thing here is always the boundary points. Why do you think it's crucial? It's crucial at the boundary points. Anybody? Why do you think it's whenever working with piecewise functions, it's always tricky dealing with the boundaries? Okay, Erica, yeah, sometimes the extreme values occur at the boundary points because, but a more general answer would be that, or a more general explanation would be that the function changes at the boundary point, right? So say to the left of -3, it's x plus 9. To the right of -3, it's x squared plus x. So you see that the boundary point is actually a turning point. It's where you get a transition from one function to another. And it's very crucial on that transition because that transition point might be a point where a cusp will occur, a sharp turn or a sharp corner can occur. So that means we need to be a little bit careful in dealing with that. So for instance, here, we see that at x equals -3, the function is undefined because from the left, the tangent of 1, from the right, the function, the tangent line has slope -5. So there's a sudden change in the behavior of the function, making the graph non-smooth. Therefore, it's not differentiable at negative. That is, the function, the derivative doesn't exist at -3. All right. Okay, so if that is clear, let's continue on. Yeah, let me just erase this part. Oops. Maybe it's easier to erase it this way. Okay, now between 2 and 5, the derivative would be just 5, right? That's the derivative of 5x minus 4. But again, we need to be careful at the boundary point x equals 2, right? And see whether the derivative exists there or not. Again, for us to circumvent the need for using the definition of the one-sided derivatives, I'm going to check first if the function is continuous at 2. So the limit of the function as x approaches 2 coming from the left will depend on this function. And the limit of that as x approaches 2 would be plugging in x equals 2, I get 6. And then let's see the limit of f of x as x approaches 2 coming from the right. That is what? That will depend on the third function. That will be 210 minus 4. That's also 6. So that means the function is continuous at x equals 2. So we can use our shortcut in finding the one-sided derivatives. So the derivative coming from the left of 2 is equal to 2x plus 1 evaluated at x equals 2, right? It's the derivative from the left, so I'm going to use the left function. Again, I can only do that because I'm sure that the function is continuous at 2, right? And that's why I needed to do this extra step earlier. And then plugging in x equals 2 to the derivative, we see that the derivative would be 5 coming from the left. And then let's look at the derivative coming from the right. The derivative coming from the right will depend on the derivative of the right function. And oops, it's also 5. They are equal to each other. Therefore, the derivative at x equals 2 is also equal to 5. Okay. Okay, I hope that's clear. Now let's find the critical numbers. Okay, the critical numbers first would be when is f prime of x equal to 0. Now we have how many pieces here? We have 1, 2, 3, 4 pieces, but luckily only one of them can be equal to 0. So we'll have 2x plus 1 is equal to 0, but we are looking for x's on the open interval -3 to 2, right? Because 2x plus 1 only apply to x's. Oops. It only applies to x's between -3 and 2. So I'm looking for the solution of 2x plus 1 equals 0 on the interval -3 to 2. And luckily, if I'll do that, I'll get x equals -1/2, which is on the given interval, right? If it happened that the x value we got, say, is equal to 5, but 5 is not on the interval -3 to 2, so that means 5 will not qualify as a critical number, okay? But luckily here, x equals -1/2 belong to the interval -3 to 2, hence it is part of the set of critical numbers. Good question, Sadia. The interval was from this. Because again, I'm looking for when is f prime equal to 0. The only possibility that f prime will be 0 is if 2x plus 1 is equal to 0. But 2x plus 1 only apply or only applies to x's belonging to this interval, right? So if you got an x outside of that interval that will make 2x plus 1 equal to 0, then that will not be a critical number coming from this source. All right. Now, and then remember, there's another source for critical. This is f prime being undefined. And f prime is undefined when x is equal to -3. And is x on the domain of f? What's the domain of f? The domain of f would be from -8 inclusive until 5 exclusive. Definitely -3 belongs there. So we can say -3 is in the domain of f. So it will qualify as a critical number based on how we defined it in class, right? I'm running out of space, so let me just resize this a bit. Yeah, there we go. Okay, so the critical numbers are x equals -3 and -1/2, right? Now we need to apply the first derivative test in order to find whether this is, or if this critical numbers will give us local extreme values. So we'll draw a real number line here, which will be divided into several parts by the critical numbers, -3, -1/2. But we also have an endpoint here. The endpoint is at -8. So let's include that for just comparison with the function value. Okay, and then the right endpoint is 5. So 5 is over here. Just to remind us that our domain is only on these intervals. And then I'll choose a test number on each of these subintervals. Maybe here I'll use -4. Here I'll use -2. Here I'll use 0. And then we plug it into the derivative. So we plug in -4. -4 will belong to the first condition. So therefore, the derivative has value 1, which is positive. And then at -2, or -2 belongs to which interval? Still this interval. Oh, sorry, no. -2 will belong here on the third condition. And here the derivative is 2x plus 1. If you plug in -2, you get a negative answer. And then 0 will belong in this interval as well. If you plug in 0, we get a positive sign, and that's it, right? And then here we know that the function is increasing from -4, from -8 to -3, so it's increasing. It hits the critical number -3, but after that it starts decreasing until it reaches -1/2, after which it will start increasing again. Okay, so that means here we will have a local maximum, here we'll have a local minimum, right? So we can conclude that there is a local max at x equals -3 with value f of -3. If we plug in -3 into the function, we'll get 6. Okay. And the local minimum at x equals -1/2 with value f of -1/2. Plug it into f, we get -1/4. Okay, and remember the boundary points also play an important role. But let's see, because there might be an absolute maximum at the boundary. But here we only have one boundary point, -8, because the other boundary is not included in our interval. So let's just check what's the function value at -8. At -8, the value is 1, but 1 is clearly less than 6. So therefore, this will not be an absolute maximum, right? So the absolute maximum actually occurs at x equals -3. So maybe I should write that down here. Since the value at the boundary I missed the F here. Then it is smaller than the function value at -3. Then -3 comma 6 is the global maximum. Actually, am I sure of that? Let's see, 5, 25 minus 4, 21. Actually, that is not true. It's not the global maximum. And let me tell you why. I thought it would be, but remember we have another segment here. So the function here is, note here, the function would be increasing as we go to 5, right? So as we go to 5, the function is increasing. It's just that 5 is not in the interval. But for x is very, very close to the left of 5, the function value will be close to 21, right? So that means the limit coming from the left of 5 would be 21. So the function values here near 5 would be also close to 21. But the function value at the critical number is only 6. So therefore, there are larger numbers here than 6. So that means the global maximum is not 6. And actually, there's no global maximum because the graph will go on until it reached 20. What was that value? Until it reached 21. To answer your question, Daniel, he's asking about, can we plug in the critical numbers instead of the numbers around it on the number line? Actually, that won't give you any conclusion, because if you plug in the critical numbers into the sign chart we're doing here, you'll get 0. I mean, you'll get the value 0 or undefined. Because remember, the critical numbers are obtained by setting the derivative equal to 0 or assuming it would be undefined. So if you plug exactly here, you won't know the sign. So you always need to plug in a number to the left and to the right of the critical numbers. All right. Well, if you'll do the second derivative test, yeah, that will be right. So if you're using the second derivative test, you will plug in the critical numbers into the second derivative. And that's basically the difference between the first and the second derivative test. The first derivative test, you need to plug in test values to the left and to the right of the critical number into the first derivative. But for the second derivative test, you need to plug in the actual critical numbers into f double prime. Okay, so I hope that's clear. But I guess here you cannot use the second derivative test. Well, can you? It might be inconclusive at the boundary because here the second derivative would be 0, second derivative would be 0, second derivative would be 0, second derivative would be 2. So on these 3 intervals, the second derivatives are all 0. And remember, if the second derivative is 0 or undefined, there are no conclusions. Yeah. So the second derivative test might be inconclusive for this test. So to answer your question, Sadia, I'm plugging into f prime. So for instance, I want to plug in -4, right? So first, I'll pick which of these conditions are satisfied by -4. So -4 will belong to this condition. So I'll be plugging into 1, but there's nothing to plug in, so the value is 1, so I got that positive sign. And then I go to -2. I'll pick which condition is satisfied by -2. -2 belongs here, so I plug in into x plus 1, and so on. So whenever dealing with conditionals, you need to check first what condition is satisfied, and then you need to plug in into the corresponding function. All right. Yeah, sure, Erica. So it would be fine. Yeah, let's do an example like this before the test. I'm not just sure about if we can do it right now, but yeah, maybe when we do the review, can you send me a similar problem or remind me to tackle a similar problem, right? So that I won't forget. Okay, it can be from the quiz. I remember, Erica, you sent me a question. I hope that made sense, that simple explanation I did. But if not, then let me know on Monday. Then I'll allot, say, 5 minutes answering another example similar to this. Okay? Because functions are very tricky to work on. So yeah. Okay, just remind me to do a similar similar example next time. All right. So any other quick clarifications? Yeah, that's a lot to digest at a single sitting. So if you still have some difficulties, you can rewatch the recording on that part and then try to answer some problems. If you encounter some problems or difficulties with certain homework problems or quiz problems, let me know so I can discuss it with you on Monday. All right. Okay, let's try problem 8. So for problem 8, same instruction, but here we have a trigonometric function to deal with. But here we are dealing with a closed interval, 0 to 2 pi. So this would be a bit tricky, or there's an additional layer to this. But still, we need to find f prime. Celia asked, will the test have questions like the one we did, like the same level? Um, as far as I remember, no. Usually exam questions are much easier than problem 7, but I won't bet on that, so I'll still prepare for something of this difficulty, just to be on the safe side. But I don't recall any test problem in the past that is of the same or similar difficulty as that one. Because you see, this problem required us to use several things from the previous chapters. So it's sort of a cumulative problem. So maybe you'll see something like this in the homework, but I doubt it will appear in the exam. But as I've mentioned, I won't bet on it. To be on the safe side, I'll try to answer a couple of such problems just to prepare for the worst case in the exam. Yeah. Okay. Now, first step, find f prime for problem 8. So f prime of x would be cosine x minus sine x, right? And the next, we need to find the critical numbers. And the critical numbers, actually f prime is defined everywhere. So the only source of critical number is to set the derivative equal to 0. That will imply cosine x minus sine x equals 0. Solve this trig function, but another way of looking at it is cosine x being equal to sine x. So basically, this equation is simply asking us when is cosine equal to sine. Of course, there will be an infinity of solution here, but we're only concerned with the interval from 0 to 2 pi. So what are those angles? So this means you need to recall your unit circle. Justin Darren is correct, pi over 4. But there's another one which lives on the third quadrant where sine and cosine are both negative. Edin, you need to adjust your second answer. It should be 5 pi over 4. Yeah. Okay, good. And then so we make a sine chart from 0 to 2 pi. Evaluate f prime of x. I have here pi over 4. Then I have 5 pi over 4. Then I'll pick my favorite special angles on these subintervals. So here I have pi over 6. Here I got pi over 2. Here say I got 3 pi over 2. Oh, I forgot this is a boundary, so let me use a solid line there. And then we plug this special angles into the first derivative because we're doing the first derivative test. If you do so, you'll get a positive here, a negative here, and a positive there. So that means from 0 to pi over 4, the function is increasing. Then from pi over 4 to 5 pi over 4, the function is decreasing. And from 5 pi over 4 to 2 pi, the function is increasing. So that means here we have a local max. Here we have a local minimum, right? So we have a local max and a local minimum, but we are working with a closed interval. So when we have a closed interval, we will use the what we call the extreme value theorem. So recall the extreme value theorem, or EVT. This tells us that if your function f is continuous on a closed interval AB, then f has an absolute maximum and an absolute minimum, which occur either at the critical number or at the endpoints, or at an endpoint, So this tells us that, well, if you are given a closed interval on which your function is continuous, then we are always guaranteed to have an absolute and an absolute max, which will occur either at the boundary A, B, or at the critical number, right? So this is peculiar to, or this is intrinsic to closed intervals. If you have a half open, half closed interval, this theorem will not apply. So this only works if you have a closed interval. So, but we already know that we have here a local max and a local min, but we need to check if we have a global max or a global min at these critical numbers. So what we do is to take the function value at the endpoints, and then the function values at the critical numbers. And it would be a contest among them. Which one, the highest one would be the absolute maximum, and the lowest one would be the absolute minimum, right? So what is f of 0? If we plug in 0 into the function f, we get 1. If we plug in 2 pi, we get also 1. If we plug in pi over 4, we'll get square root of 2. If we plug in 5 pi over 4, we'll get negative square root of 2. Okay, so these 4 values were obtained by plugging into f. So these values tell us that the absolute maximum, and as we have mentioned, the absolute maximum would be the highest point on the entire closed interval 0 to 2 pi, and based on these values, the highest will occur at pi over 4 comma square root of 2, right? But remember that the pi over 4 we have already concluded earlier will give us also a local maximum. So this is also a local maximum, which is also a local maximum is at pi over 4 comma square root of 2, while the lowest value is our absolute minimum. And it is also a local minimum is at 5 pi over 4 comma negative square root of 2. All right. And since the endpoints gave us neither the highest or the lowest function values, then there would be no conclusions for them. They cannot be local maximum or local minimum because there is no neighborhood. Because remember, they are the endpoints. So there are no function values to the left of 0 and no function values to the right of 2 pi. So yeah, so we won't make any conclusions about them. But it can happen that the highest value will be on one of the endpoints, right? Okay, so this is what the template for working with closed intervals. So you always need to compare the function values at the critical numbers with the function values at the endpoints. Whichever one is the highest, the global or the absolute maximum, and the lowest would be the global or absolute minimum. I think, Sadia, what you meant is when you are in a closed interval. So in a closed interval, you will always have an absolute maximum and an absolute minimum value. Other term for absolute maximum value is also the global maximum value. And here's the absolute or global. And this is not to be confused with the absolute value. So this is the absolute maximum, which means the highest, all throughout the closed interval. Sometimes you call it the global max. And the absolute minimum is the lowest value on the entire interval, hence the alternative term global. Okay. Okay, does that make sense? Any questions with problem 8? Okay. Now let's proceed. I guess this